the introduction. I'm from the Zurich University of Applied Sciences, and I'll show you something about the fusion of a 3D time-of-flight sensor with an RGB camera. First, for the motivation, a 3D time-of-flight camera can capture a depth map, and it's very easy to use, but it has a low resolution, and so we perform fusion with an RGB camera to increase that resolution. And if we apply image interpolation on a 3D TOF depth map, that works very well on smooth surfaces, but not around edges. That's why we use an algorithm to extrapolate on these edges. We built a fusion hardware that consists of an Espros 635 3D TOF camera and a Raspberry Pi camera version 2. And the TOF camera has a resolution of 160 by 60 pixels, and we can upscale that by a factor of 16 in both directions, so we achieve a resolution of 2560 by 960. We also created a data set that consists of captured 3D TOF depth maps, RGB images, and they're aligned, so they show the exact same section. And we created a ground truth depth map from a 3D simulation. So there's a data set consisting of 3 different images. This is one example that's like a paper dodecahedron. It shows just a geometric shape to test our algorithm. Then for the algorithm, we first start by performing image interpolation. So here you can see an example not from our data set, but from the Middlebury 2005 data set. An RGB image and the captured disparity map in this case. So it's not depth values, but disparity values. It's usually used on a stereo vision, but our algorithm works just as well on these images. And we first perform image interpolation to get the depth image to the same resolution as the RGB image. And as a next step, we do edge detection. And if we do that on the depth image that was upscaled, we get very blurry edges, obviously because of the interpolation. And if we use the edge map that we get from an RGB image, we get too many edges. A typical example of that is text on a surface, like this crayon here has text on it, but we don't want an edge in our edge map because the depth values are the same across that surface. So we do a joint edge extrapolation, joint edge detection to get only the edges that are relevant in the depth map, but that are also sharp. And then the next step would be edge extrapolation, which I'll explain here. We perform this action in all 4 cardinal directions, up, down, left, and right. And basically what we do is so we take pixels next to an edge in one direction, like for example here, starting at this edge over to the left, and we remove them from the upscaled or from the interpolated image. The graph on the right is a single line from the image on the left, and the pixels that we removed here are the ones that are bad. You can see the image or the green line does not follow the blue line correctly. There's this smooth, it goes up smoothly, even though there should be a step. And that's why we remove those pixels. And then we take the original captured pixel values from the 3D TOF depth map, and we use that to fit a polynomial up to the edge, and that way we can improve the sharpness of the edge. Now for some results, here you can see the RGB image and the ground truths from our data set. There's also the captured THAW depth map, our results, and a result of another state-of-the-art algorithm. And what you can see is that there's the edges in our algorithm are quite a bit sharper than in the competing algorithm. Another thing you can see here when we look at another row of pixels is that the overshooting that appears, or also the just pixels that were captured that were not correct in the 3D THAW image, don't appear in ours after we apply our algorithm. But in the competition, there's these zigzag lines in some places, especially around the edges. Then for some numerical results, for the root mean square error and mean absolute errors on our data set at the top, and for the Middlebury 2005 data set at the bottom. In the Middlebury data set, we don't perform quite as well as another state-of-the-art algorithm, but on our own data set, it's quite performing better. And that's mostly due to the noise that we can also reduce that's apparent in the 3D THAW images. And another measure we used was an effective upscaling factor, which is supposed to measure like how much further away a robot could be from an object and still see the object more clearly. Like here we have the 3D THAW depth map at 120 centimeters, and if we upscale that by a factor of 16, the perceived quality is somewhere or almost the same as like at 50 centimeters or at 30 centimeters, or it lies in between those two images. So you could say that if a robot were at 120 centimeters from a target, it would see the object as clearly as if it were around between 30 and 50 centimeters from that object. So we say we achieve an effective upscaling factor of around 2 to 4. Obviously, this is a very subjective measure of the quality of our algorithm. For the conclusion, our edge extrapolation algorithm has a low computational complexity, and it produces very sharp edges, and it can perform as well as other state-of-the-art algorithms. One of the problems is that it still suffers from various artifacts. And for an outlook, what we could do to improve is perform the extrapolation in the direction of the edge gradient instead of just performing it in 4 directions. So we would get only the relevant directions. Another thing we're currently working on is a real-time implementation on an IMX8 system on module. And another thing we would like to do is to combine this with 3D THAW multipath interference separation and improve the accuracy of the depth maps. And we have shown that last year at Sensors with a paper on multipath separation. So thank you for your attention.